Hi everyone, welcome back. In the last video we talked about cylindrical and spherical coordinates, and now let's actually set up some integrals in cylindrical coordinates. So for these integrals, just like with triple integrals and Cartesian coordinates, the hardest part is setting up bounds. But the other thing that we need to be aware of or take care of before we start integrating is what to do with dv, or what do we need to multiply our functions by, or this element we multiply our functions by is called a Jacobian. So what is the Jacobian for cylindrical coordinates? Well, dv in Cartesian is just dx, dy, dz. In cylindrical coordinates, it's r times dr, d theta, dz, where r is just exactly the same as it was in polar. So I'm not going to go through the derivation of this. It's similar to what we did in polar coordinates, just now we're talking about volumes instead of areas. But the idea is if you switch from Cartesian to cylindrical coordinates, you need to multiply your function by r when you integrate. So in other words, I have this integral of some function f over some solid, and f is in Cartesian coordinates, x, y, and z. If I want to write that in cylindrical coordinates, I'm integrating over the same solid, but now I replace x with r cosine theta, I replace y with r sine theta, z stays z, and I have to multiply my function by r. That's the important thing to remember. So that means volume. In Cartesian coordinates, when we want to find volume, we just integrated 1. In cylindrical coordinates, we integrate r to find volume. Let's do an example. So integrate the function 4z over a solid E, where E is bounded by the ellipsoid 4x squared plus 4y squared plus z squared equals 16. That's above the xy plane, and it's bounded by the xy plane. So what does this solid look like? I've drawn it here. We can take a look at it. The xy plane is the bottom bound for the solid, and this ellipsoid is the top bound for this solid. I also have this in Mathematica, where here's the solid here. So let's look at this while we decide how we want to integrate. I'm definitely going to use cylindrical coordinates, because that's the whole point of this video. But do we want to integrate with respect to theta, r, or z first? We could always integrate with respect to theta first, that's fine, but if it comes between r and z, let's integrate with respect to z first. Why? Because if I look at this object, and I think about traveling through this object in lines parallel to the z-axis, there is a clear bottom bound, the xy plane, z equals 0, and there is a clear top bound, this ellipsoid. So if we integrate with respect to z first, I'm going from the xy plane, z equals 0, to this ellipsoid, which we have an equation for. So if we go back to our notes, we can solve this ellipsoid equation for z. Since I'm only using the part of the ellipsoid above the xy plane where z is positive, I can just take a positive square root. Now I need to change this to cylindrical coordinates, so I replace x squared plus y squared with r squared. And so this ellipsoid is z equals the square root of 16 minus 4r squared. And then I just factored out a 4 and took a square root. You don't have to do that. But this ellipsoid is 2 times the square root of 4 minus r squared. So z in this solid is bounded below by 0 and bounded above by 2 times the square root of 4 minus r squared. And we have our z bounds. Once we have our z bounds, we just need to project this solid into the xy plane. And what we see is a disk of radius 2 centered at the origin. If you've gotten the hang of double integrals and polar coordinates, then it's easy to set the rest of our bounds here. R just goes from 0 to 2, and theta goes from 0 to 2 pi. So the only other thing we need to remember is when we set up this integral, the integral of 4z over the solid, that we multiply our function by r. So 4z gets multiplied by r. Our z bounds were from 0 to 2 times the square root of 4 minus r squared. R went from 0 to 2, and theta goes from 0 to 2 pi. Now we can partially separate this integral. We can't completely separate it. So we can separate it in theta, but not r. So first of all, if I look at my function, I have a product of a function of z times a function of r, and I can think of 1 as a function of theta. So it is separable. The function itself is separable. And I don't have any thetas in my bounds, so I can separate this d theta all the way out. But I can't separate r. I can't pull this dr over here because I have an r in one of my bounds. If you have r's in your bounds, I can't separate the r and the z integral. I have to integrate with respect to z and then r to make sure I have all the r's before I integrate. But I can partially separate it, so let's go ahead and do that. So I rewrite this integral as a single integral times a double integral. And so this integral is just 2 pi And here I'm integrating with respect to z first, so I integrate that to get 2z squared r. And I evaluate from 0 to 2 times the square root of 4 minus r squared. So it really didn't matter that I factored this 4 out and took a square root to make it 2, because I'm going to end up squaring it again. And I'm going to just distribute that 2 back through when I square it. So when I plug this bound in and I square it, I get this 2r, that was the 2 and the r from here, times 16 minus 4r squared. And now what I'm going to do is I'm going to factor this 2 to the left to make this 2 pi 4 pi, and then factor or distribute this r to the right to make this 16r minus 4r cubed. And now I just have an integral in r. You could also factor a 4 out, another 4 out, but I'm going to leave it here this time, not factor it out, so that when I integrate, I don't have any fractions. Because when I integrate, this is going to become r to the 4th. I have to divide by 4, and then that 4 is just going to cancel out. And I get 8r squared minus r to the 4th. I plug in my bounds and end up getting 64 pi as my answer. Okay, let's look at another example. Find the volume of the solid bounded by the cylinder x squared plus y squared equals 1, the xz plane, the plane z equals 4, and the sphere x squared plus y squared plus z squared equals 1 in the region in space where y is less than or equal to 0. Okay, so I've drawn all of these surfaces here, and this is more or less what this solid looks like. We're in the region where y is less than or equal to 0. This half disk is the plane z equals 4. We see the cylinder, x squared plus y squared equals 1, kind of going down this solid. Here, this is in the plane xz plane where y equals 0. And down here I have this piece of the sphere, x squared plus z squared, x squared plus y squared plus z squared equals 1. And I want to find the volume of the solid. I also have this in Mathematica if you just want to take a look at it, a better representation of this. And so this is the solid that I want to find the volume of. We could use geometry to find the volume of this solid, find the volume of the cylinder, and subtract the volume of the piece of the sphere. So find the volume of this half cylinder and subtract this quarter sphere, quarter ball. And that would work. But let's use triple integrals just to get used to using triple integrals. So the key here is setting up bounds. And do I want to set up bounds for r, theta, or z first? Theta you can set up first, that's no problem. The real question is, do I want to set up bounds with respect to z first or r first? And here there's a clear winner. Because if I set up bounds with respect to r first, I'm going to need to set up 2 different integrals. And you can see that in this region, r is starting at the origin, going all the way out, or sorry, r is starting at the z-axis and going all the way out to the cylinder. So r goes from 0 to 1. But in this region with the piece of the sphere, r is starting at the sphere and going to the cylinder. Maybe this is better seen in the notes. Right, so r is starting at the sphere and going to the cylinder in this region. So if we integrate with respect to r first, or rather just integrate with respect to r before we integrate with respect to z, we have to set up 2 integrals. That's not the case if we set up bounds for z first. So if we set up bounds for z first, z just goes from the sphere to this plane z equals 4. So all we need to do is represent the sphere in cylindrical coordinates. So we replace x squared plus y squared with r squared, subtract, take a square root. Again, this sphere, just like the last example, was where z is positive, so we only need this positive square root. So this is the sphere, the square root of 1 minus r squared, and this is just the lower bound for z. The upper bound for z is just 4, because this is plane z equals 4. So we have our bounds for z. Then we project this solid into the xy plane. It's just in the xy plane, it's just going to be half of a disk in the 3rd and 4th quadrants. So r goes from 0 to 1 in that disk, and theta goes from pi to 2 pi, because it's just, this is the negative x-axis, where theta is pi, and then we want to come around to the positive x-axis, where theta is 2 pi. So now we have all of our bounds. We set up our integral. It's a volume integral, so we're just integrating r, because remember in Cartesian that would be 1, but we switched to cylindrical, we're integrating r. In theta, we went from pi to 2 pi. In r, we went from 0 to 1. And in z, we went from the sphere, the square root of 1 minus r squared, to 4. The plane z equals 4. So this integral, again, we can't completely separate, but we can pull out the theta. So I'm going to do that again. Pull this d theta through. I can't pull the dr through because I have r's in the bounds here, but I can pull the d theta through to evaluate this integral, and then I have this double integral left over. So in theta, I just get 2 pi minus pi, which gives me pi. Here I integrate with respect to z. Then I plug in my bounds. So I have pi times the integral from 0 to 1 in r of 4r minus r times the square root of 1 minus r squared. So there are my bounds in c, just multiplied by this r. And now 4r is no problem. I just need to do a u substitution for this term. So I let u equal 1 minus r squared. Du is negative 2r dr. So I have the negative and the r already there. I just need to multiply and divide by 2, or multiply by 2 and multiply by a half. And then I'm going to have 1/2 u to the 1/2 du. So I integrate that. 4r becomes 2r squared. Here's the 1/2 I have left over from the u substitution. 1 minus r to the 3/2 divided by 3/2, which is multiplying by 2/3. Plug in my bounds, and I get 5 pi over 3 as the volume of that solid. Alright, so there's a couple of examples of triple integrals in cylindrical coordinates. In the next video, we'll do triple integrals in spherical coordinates.